Now in question number 6, we look at Le Chatelier's principle, more stoichiometry, and all about the Kc. So this question goes, the dissociation of iodine molecules to iodine atoms is a reversible reaction. I can actually already see that this is a reversible reaction by looking at this arrow right over here. And it's a reversible reaction taking place in a sealed container at 727 degrees Celsius. The balanced equation for the reaction is then given. Now, very important when you're looking at the Kc, Le Chatelier, and so forth, looking at your mole ratios, because we know that temperature, pressure, and all those things is very important, and as well as the moles of the balanced equation. We are then further told that the Kc for the reaction at 727 degrees Celsius is 3.76 times 10 to the negative 3. Most of the time they ask us to calculate the Kc. Now that they've given us the Kc already in my mind, I can already see that we're going to have to then work backwards. Now, number 6.1 says, write down the meaning of the term reversible. Now, reversible is not like a jersey that is reversible. In chemistry, it means something completely different. And that this means that products can be converted back to reactants. Products can be converted back to reactants. That is then what reversible means in chemistry. Number 6.2 says, at equilibrium, very, very important. At equilibrium, the pressure of the system is increased by decreasing the volume of the container at constant temperature. Now remember that when we then increase or decrease pressure, according to Le Chatelier, the system will shift in such a manner as to counter that stress. Now the following continues to say, how will each of the following be affected? Now remember, the pressure is increased by decreasing volume. So now we must choose only increase, decrease, or remains the same. The first one says the value of the equilibrium constant. So what happens when we increase pressure by decreasing volume, and what happens to the equilibrium constant? It remains the same. It remains the same. Let me go down. Let's look at the other one. Again, at equilibrium, the pressure of the system is increased by decreasing the volume. We must also choose increase, decrease, or remains the same. What will happen to the number of moles of the I2? Now, this one will definitely change. This one will then increase. This will increase. When we increase the pressure by decreasing volume, this one will then increase, meaning that the reverse. Let me just go up, all the way up. It means that this will then increase. Let's go down. So number 6.3 says, explain the answer to question 6.2.2 by referring to Le Chatelier's principle. Now, talking about Le Chatelier's principle, you must talk about the pointers that Le Chatelier says, the same way we used when we talked about the collision theory. Now, this is very crucial because when we increase pressure, now remember, pressure is increased by decreasing the volume. When we increase pressure, the reaction that leads when we increase, let me just check there. Leads to the smaller amount. Leads to the smaller amount of gas molecules. Molecules is favored. And then what this means, therefore, the reverse reaction is favored. So when we increase the pressure, the side with the smaller gas molecules will then be favored. Let me just go up. So let's see, between the two, I can see here I had 2 moles and here I only had 1. So when we increase the pressure by decreasing the volume, the reverse reaction is favored because it has the least gas molecules. It only has 1. And that is then the side of the equation that is then favored. Let's look at number 6.4. It says at 227 degrees Celsius, the Kc value for the reverse reaction above is therefore 5.6 times 10 to the negative 12. Is the forward reaction then endothermic or exothermic? And must fully explain our answer. This means therefore if it moves from 3.6 to 5.6, this means then it becomes endothermic. It is an endothermic reaction. Now, endothermic and exothermic reactions is again grade 11. But now the Kc, they say fully explain your answer, and this is for 4 marks. Now let's talk about what actually affects endothermic and exothermic on the Kc. So Kc value decreases with temperature decrease. With temperature decrease. And I can see because now my temperature is 227. Initially, I just want to go all the way up. Initially, my temperature was 727. So I can see that the temperature decreased. So a decrease in temperature will decrease the Kc value will decrease with temperature decrease. And what else happens? We then favor the reverse reaction. The reverse reaction is favored. Reverse reaction is favored. And then a decrease in temperature favors the exothermic. Decrease in temperature favors and let me just say an exothermic reaction. You could have done it the other way around by saying with a temperature increase, here we said with a temperature decrease, we could have said with a temperature increase, the forward reaction is then favored, and then increase in temperature favors the endothermic reaction. So we could have done it like that as well. But we're not going to get penalized for writing it like this. And then here is question number 6.5. So it says a certain mass, we don't know what mass this is, so an unknown mass of iodine molecules, which is I2, I can already see that it has a mole ratio of 1, is sealed in 12.3 cubic decimeter flask at a temperature of 727 degrees Celsius. The Kc, usually we are looking for the Kc, but the Kc is equal to 3.76 times 10 to the negative 3. Now, when equilibrium is reached, the concentration of the iodine atoms is found to be 4.79 times 10 to the negative 3 moles per cubic decimeter, which is concentration, very important. We must calculate the initial mass of the iodine molecules in the flask. Very crucial, you need to first have a balanced equation. I'm going to write it here so I can work half-half on my paper. Remember, our initial reaction equation looked like this. It's 2I and then G. So I had a mole ratio of 2 is to 1. It was a reversible reaction. Now, the nice thing about this question is I'm already given the Kc. Remember, when you're finding the Kc, it's always your products. It's always your products over your reactants. So we also use solid brackets. I'm going to do it the long way around. R. So my products is I'm going to have I2 here at the top. Remember, the 2 in front becomes an exponent. And then I'm going to have my reactants here at the bottom, which is just a 2. Now I'm told that the Kc value is 3.76 times 10 to the negative 3. Now I'm told that the concentration of the iodine atoms, remember for Kc we use concentration, is 4.79, so I'm going to have this one here, 4.79 times 10 to the exponent negative 3. Remember, I do have an exponent 2 outside, and then I'm going to find the value of this I. So this is just mathematics. And I'm going to then cross multiply. I'm going to cross multiply. Let me take this off, and then I'll come back and write on the side so that you can just see what I'm writing. So I'm just going to cross multiply. I'm just going to put a 1 there. I'm going to take that multiplied by 1. I'm going to have 4.79 times 10 to the negative 3 exponent 2 equals, I'm going to have all of this multiplied by the I. I'm going to keep everything in brackets because, I don't know, if you don't keep it in brackets, then the calculator does exponents first. And that is now I2. I'm looking for I2 by itself, so I'm going to divide both sides with what's bothering the I2, which is 3.76 times 10 to the negative 3. What you do on the one side, you have to do on the other side, times 10 to the minus 3. This side and this side will cancel, leaving me with my I2. So I'm going to put it in the calculator exactly as it is. Let me put it on this side. I'm going to put brackets around it. I'm going to get 4.79 times 10 to the exponent negative 3. Remember, I do have a squared bracket. And at the bottom, I've got 3.76 times 10 to the exponent negative 3. There we are. So there, that's what I get. So I'm going to move my comma. I'm going to move my comma 3 times. So I have the 6. I'm going to say 1, 2, 3. So I'm going to leave it as 6.1021 times 10 to the exponent 3. I've just moved my comma 3 times. Just going to keep it like that. I'm also going to keep it to 3 or 4 decimal places because this is not my final answer. Remember, the more you round off, the more kind of incorrect your answer actually becomes. So that is then what I get for my concentration of my I2. Let me just extend my page a little bit. So therefore, I'm not done. We're still looking for the mass. I haven't even started with the question. I'm going to go back. This was my reaction. Just want to write this down for you so that when we talk about mole ratios, you know exactly what I'm talking about. This will be 2I and then G. So now I like using the start table. I don't know, your teacher could have taught you how to use either one. I use initial, change, and then equilibrium. Initial, change, equilibrium. I'll just scroll up if I need to. I draw my table like this. I'm going to break it up like that. So now this is for this table respectively, for this one respectively. Now remember, this is the reactant. At the change, the reactants are being used up. But at the change, the products are being formed. Reactants get less while products are being formed. I was told that my I at equilibrium was 4.79 times 10 to the negative 3. Now remember, I just calculated my equilibrium constant for this one, my concentration for my I2, which is here. So I'm going to say 6.1021 times 10 to the negative 3, right? Let me just write mole dm3 to show that that's concentration. Initially, I didn't have any products because remember, when you start a reaction, you've got no products, only reactants, right? So that would be 0. Now 0 plus 4.79 times 10 to the negative 3 will give you 4.79 times 10 to the negative 3. Now we're going to have to use mole ratios. This is how this works. Here I've got 2 moles. So 2 moles is equal to 4.79 times 10 to the exponent 3. I want to find how much was 1 mole. if 2 moles is 4.79 times 10 to the negative 3, I'm going to divide that by 2 so that I can find the value of 1 mole, which will come here. So let's calculate that. I'm going to take my calculator. Let me just move it on the side. So I'm going to take this 4 because it did say at equilibrium, which is 4.79 times 10 to the exponent negative 3. This is 2 moles. I want to find the value of how much was 1 mole. I'm going to divide that by 2 to find the value of 1 mole. So there I found my 1 mole. I'm just going to move my comma again to have it by the point 2. My comma starts there, 1, 2, 3. I'm going to have 2.395 times 10 to the negative 3. I just want to keep it like that. So that will be 2.395 times 10 to the exponent negative 3. Now remember, I don't know what I had initially. I know that I've used up 2.39 times 10 to the negative 3, and at equilibrium, this is what I was left over with. Now, I need to find what I had initially. Now, this is just mathematics. If you've used this, and this is what you've left over, it means the sum of these two is what you've had initially. So I'm just going to add them together so that I can find what I initially had. I'm just going to write it in this manner. 2.395 times 10 to the exponent negative 3. And I'm going to add the 6,01021 times 10 to the exponent negative 3. I do put brackets around it. It just makes it easier. There we are. So I'm just going to move my arrow again so I have it by the 8. 1, 2, 3. So I'm going to leave it as 8.4. 9. So I'm going to leave it as 0,8405. So that's what I had at equilibrium times 10 to the negative 3. 8, let me just 8,405, I've got 405 times 10 to the negative 3. So that is what I had at equilibrium. Just want to go over this again. Remember, this is what we had at equilibrium, but this was the value of 2 moles, right? If you have a value of 2 moles, you need to find the value of 1 mole, right? So for me to find 2 moles, I'm going to have to divide this by 2 so that I can find the value of then this one. So that is why I divided it by 2. And then for me to find what I initially have, if this is what I've used up, this is what I had left over, the sum of these two is what gave me this. I'm just going to work on my side so that we can therefore calculate the mass. We are not done yet, right? They did say they want the mass. So now let's move along. I am going to use the formula. I'm going to use the formula. I don't know if I can move there. Now, let me rather move down so that we have enough space. I'm going to use the formula C is equal to M over my big M and then V. I'm going to use this one because I do have the concentration. I'm looking for my mass. I do have my molar mass as well as I do have my volume. Remember, they told me it is in a flask which is 12.3 cubic decimeters. So I do have all of that information, and this is the one I am therefore looking for. I'm going to make M the subject of the formula. I'm going to put this over 1, cross multiply. M times 1 will give me M, and then I have my concentration multiplied by all of this, which will be my molar mass, and then my volume. Now remember, my concentration, they said they wanted the initial mass. This is the initial mass that I had, right, before the reaction. So that's then the concentration I will use. Therefore, I got 8,405 times 10 to the negative 3. And then I need to find my big M. Now remember, iodine is 127. So my I2 is equal to 127 on the periodic table. I've got 2 of those. So I just multiply this by 2, and then I'll find my iodine in grams per mole, which is 254. Okay, I just did that in my head. Now the volume that I was given was 12.3 cubic decimeters. Now I'm going to find my mass. I'm going to put everything exactly as it is, and then we should get our mass. Remember to put brackets around everything. I'm going to have 8.405 times 10 to the exponent negative 3, right? That is the initial concentration, 254, and I must multiply it by the volume in which the container was, which is 12.3, equal to, and therefore I get 26. Remember, the third number will change this one to then a 6. So I'm going to get 26, 26. The SI unit for M is then a small g. I think the most important thing that you needed to find out here was this part here by dividing it by 2, and then to remember that they were looking for the initial mass, which you had to find by the initial concentration before equilibrium was reached. Now, it's very important that you actually do practice a lot of Le Chatelier's principles. It is a lot of mathematics, and it's also a lot of mole comparison and stuff, but you'll see once you actually get the hang of it, it's actually pretty easy, but you must make sure that you read your formula or your equation properly and then see everything that you're given. I like using this table, the ICE. Some teachers use the start, some teachers use the in, out, and however, whatever your teacher has used you or taught you to use, stick with that one, but practice as many as you can. They can be a little bit challenging, but they're fairly easy.